Okay, so today we start with another important topic, which is the generation and recombination of carriers. If you recall, this is one of the slides that we've been looking at, which describes the analysis of general structure of analysis of a semiconductor device. And apart from the equations that you see here, we said that we need to understand doping, we need to understand mobility and diffusion constants, and then generation recombination. These are the terms that enter into my equations here. And so once we have models for all of these, then we are in a position to use these equations to understand semiconductor devices. All right, so let's look at then the generation and recombination. And the ideas are very simple. You have a device, and let's say you want to calculate a current at a particular point. Let's say this is the plane where you're wanting to calculate current. And to calculate current, you know that you require the carrier density. Now, the carriers at this particular point, at this particular plane, where can they come from? I have to understand what the number of electrons and holes are. Where can they come from? Well, we just saw doping. Because there's doping, the doping will introduce carriers at this particular point. Where else can they come from? Well, when you apply a voltage, what can happen is carriers from one point can get injected into this particular point here. So carriers from one place can migrate, obviously, to the other place here. So you get carriers at this particular point due to injection process here. So that's one. The other one, of course, is that you can have generation. Right at this particular point, you can have an external source which generates carriers here. So that's called generation. And of course, carriers can disappear also because of recombination. Okay, so we have to understand, you can see that if you would like to know what the carrier density is at any particular point, you have to know what the generation rate is at that particular point. You also have to know what the recombination rate is. Okay, it may happen in some cases, net generation rate is 0 or net recombination rate is 0, which is okay. But in many cases, you may find that there is a generation rate, there's a recombination rate that you need to take into account. So generation and recombination are, as you understand, what you are doing is you're creating a electron in the conduction band and a hole in the valence band in the generation process here. And in the recombination process, the electron here is recombining with the hole here, and then it leads to disappearance of both electron and hole here. As you can see here, generation would require energy because you're promoting an electron from the valence band to the conduction band, so it requires energy to do that. Recombination, on the other hand, releases energy. So as things recombine, energy is electron as it drops from higher energy to a lower energy level, it releases energy. So there are two broad mechanisms. The absorption of energy or release of energy could be thermal in nature, or it could be optical in nature. Optical in the sense that the energy that is absorbed to create an electron hole pair can be a photon, and energy which is released when an electron and a hole pair recombines, that can also be a photon. Okay, so these processes can take place mediated through a photon, or these processes can take place mediated through thermal energy here. In any case, in equilibrium, you expect that generation and recombination would balance each other, and therefore the net G minus R, net rate G minus R will be 0. All right, so then let's look at these mechanisms which cause generation of carriers, mechanisms which cause recombination of carriers in a little bit more detail. There are different mechanisms that do that. We'll look at we'll look at generation first, and we look at, as I said, optical generation. Okay, optical generation, and so optical generation, generation of carriers takes place because the photons are absorbed, and the way we model it is a very simple equation which is given here. So the idea is that you have certain light intensity, I naught incident on your semiconductor. As the light intensity, as the light travels through the semiconductor, the photons are absorbed and the light intensity decays. And if the semiconductor is thin, some light may come out of the other side. If the semiconductor is thick, almost all the light will get absorbed. Obviously there's also a possibility of reflection here. You will have metals here, so it may reflect the light back into the semiconductor. You have reflection at this particular point here also. Okay, so we model it using a very simple equation which tells that the light intensity as you go inside the semiconductor decays exponentially. So Ix at any particular point is equal to the incident light intensity here, exponent minus alpha x here. So alpha is what, as you can see here, units of 1 by centimeter is what we call as the absorption coefficient. So for a semiconductor, alpha is what absorption coefficient is what describes how photons are absorbed in that particular semiconductor and give rise to electron hole pairs. Okay, so the key parameter here is the absorption coefficient. And from this very simple equation, you can see here that if you would like to absorb 90% of those incident photons, again, I'm neglecting the reflection part, assuming that, we're talking about I naught as the intensity which gets into the semiconductor. Okay, not the total incident, because of the total incident, some will always get reflected because of mismatch between the refractive index. Refractive index of air is 1 and refractive index of semiconductor is something else. So there will always be a reflection component. I'm not talking about that. Okay, I'm talking about the intensity. I naught is what intensity gets into the semiconductor here. So I naught is intensity at x equal to 0 plus, which means just inside the semiconductor. Okay, so keep that in mind. All right, so absorption coefficient is the key parameter which describes how carriers get absorbed inside a semiconductor. And you can see here, we need a thickness of, for 90% absorption, we need a thickness of 2.3 by alpha here. All right, so this is optical absorption here. And you all know that I need a minimum energy of the band gap. My photon must have an energy at least equal to the band gap to excite an electron from the valence band to the conduction band here. Okay, so it's not that any light which is incident will get absorbed. If the light has energies much smaller than the band gap, the material is going to be transparent to that particular wavelength. The light is just going to pass through. Okay, so energy gap decides the highest wavelength which will get absorbed. And how do we calculate the highest wavelength? Well, all of you know the simple relationship E equal to h mu c by lambda here. And as I said, minimum energy required to promote an electron from valence to conduction band is the band gap. So band gap is 1.12 for silicon here. And if we put this, we find that the maximum wavelength that will be absorbed is 1105 nanometer for silicon. All right, let me show you now. So alpha that you see here is the absorption coefficient. Let me show you how this absorption coefficient depends on lambda. Of course, absorption coefficient for lambdas larger than 1105 will be, absorption coefficient would be what? 0 or almost like negligible. Okay, so let's look at the absorption coefficient then. All right, before we do that, when we talk about optical generation, or absorption, we said that the concept of direct and indirect band gap is important. Okay, so this is the picture of silicon that we have. Silicon, we said, is an indirect semiconductor in the sense that the top of the valence band and the bottom of the conduction band here are at two different K values here. And that's why it's indirect semiconductor. We also said that a photon, if you calculate, the momentum of the photon is almost negligible. So if you want a photon to take an electron from here and promote it here, a photon cannot do that. Because remember, in that whole process, the momentum also has to be conserved. And we said h bar k, whatever k value is here, is like momentum of an electron. Okay, it's like a momentum of an electron. So now if you simply absorb a photon, my electron is not going to go here. In fact, if you absorb a photon, it may go somewhere here, but I don't have any state. If you absorb 1.12, then I don't have any state at 1.12, so it can't go here, right? So the way it happens is, the way an electron can still go here is that the absorption then becomes a process which involves not only an interaction of photon with an electron here, but it also involves a phonon, a lattice vibration. And phonons we have seen are available. They can be available with very high momentum values here. So along with that, a phonon is involved, and which phonon helps to translate the momentum part. Phonon doesn't carry that much energy. For example, I may have a electron, I may have a photon of energy 1.12, and the phonon energy may be only few milli-electron volts, maybe 10 milli-electron volts, 15 milli-electron volts or so. So phonon energy is less, but phonon can supply a large momentum here, this here. So in the absorption process, I have a photon coming in and have a phonon also coming in. And together, then, they can promote an electron from here to here, and I get absorption. But obviously, because now I have the requirement of a phonon also, the process absorption then becomes inefficient. The interaction of photon in taking an electron from here and promoting it here is not very efficient because it requires the presence of another entity, another phonon. Phonon has to be present of the right, phonon has to be there of the right wave vector to cause a translation in momentum. So that's why absorption is not very efficient in silicon here, but it absorbs. And therefore, what would you expect? You would expect absorption coefficient to be small. Absorption coefficient to be small here, okay, in silicon. But note that as you keep on increasing the energy of the photon, 1.12 is here. But then as you keep on increasing the energy, a stage comes when you're illuminating your sample with 3.4 eV. Now what happens is the electron can make a transition directly here, right? It becomes a direct transition. And now you would see, at this point, you would see a very large absorption coefficient because you don't require a phonon now. And a photon can simply come in, take an electron from here and promote it over here. Okay, so now you, in that case, you'll see absorption, which is stronger here. Anyway, I don't want to get into the details, but I want to show you how the absorption coefficient goes with wavelength. Look at the picture here. This point somewhere here is about, as I said, 1100 or so. So absorption falls to negligible values here. So this is where the limit set by the energy gap. Then the absorption coefficient is rising. I'll not go into the details why it rises here, but then, it has a certain behavior that you see here. So absorption coefficient, the message here is 2. One is absorption coefficient in general is a function of wavelength. What wavelength is incident on your semiconductor, the absorption coefficient depends on that. Okay, so you can see this behavior here. The other one is, for silicon, you can see the absorption coefficient is, the values that you see here are low. For example, if I'm at, say, 800, probably I see something like 10 to the power 3 here. I mean, low in the sense, a good value is something, a moderate to high value is somewhere around 10 to the power 4 or higher. Okay, so these are the values. This is the point, this line that you've seen here. This is the point which corresponds to, this wavelength corresponds to 3.4 eV, where I have direct transition here. So you can see here very high absorption coefficient is there. Now, what are the implications of this kind of a graph here? Well, absorption coefficient like this, it means that if I have a light of, let's say, 900 nanometer or so incident on my silicon, you can see here absorption coefficient is 10 to the power 3, let's say. 10 to the power 3, which means what is the thickness of silicon that I require to absorb the entire light? 2.3 divided by 10 to the power 3, right? So it would be 23 microns, right? 23 microns of 23 micron thick semiconductor I require to absorb the entire photons which are incident, which have an absorption coefficient of 10 to the power 3. All right. Now let's look at, all of you know that silicon is widely used as a solar cell material, where the whole idea is to absorb photons and convert them into power. What is the solar spectrum that is incident? Well, this shows the solar spectrum here. Okay. What does this graph show? Well, on the x-axis we have the wavelength, and this one shows, normally the solar spectrum is represented in many different ways. In this case, I've represented it by number of photons which are incident per centimeter square per second in a certain wavelength range here, per nanometer range here. Okay, so this is the kind of a spectrum that we have. Expressed in terms of number of photons. Sometimes people express it in terms of the power in watts incident per centimeter square per nanometer and per second here. Now, what do you notice about this particular spectrum here? I have a lot of, so when you're making a solar cell, you would like to absorb all the photons. All the photons that are incident on your semiconductor, you would like to absorb all of them and then convert them into energy, right? But then what will silicon do? Silicon absorbs from where? From 1100 or so, right? From somewhere, 1100 is somewhere here. So it absorbs from 1100 nanometer and below that. Above 1100 nanometer, all these photons that you see here will not get absorbed. That's the one problem. Okay, so which translates into roughly 38% of the incident photons are not going to be absorbed by silicon. All right, those are lost. Why? Why are they lost? Because of the energy gap itself. The energy gap limits the wavelength that you are absorbing. Even otherwise, when I go, let's say 1100, let's say if I go 1000, at 1000 nanometer, you can see I have a lot of photons which are incident, right? Now at 1000 nanometer, what do we find? What is the absorption coefficient? Maybe 10 to the power 2. 10 to the power 2 means how thick a silicon do I want to absorb? Go back here, 10 to the power, this is 10 to the power 2, right? And these are all in centimeters. So 10 to the power 2 means 2.3 into, you're talking about very large, very thick silicon in terms of microns, 200 micron or even larger. Very, very thick silicon. All right. Now, the thicker the silicon is, the more expensive the whole thing gets here. Okay. The substrate in a solar cell, the silicon substrate costs a lot. Okay. If I could make a very thin silicon and also absorb, then that would result in reduction in cost as well. So what you're seeing here, the implications are that because the absorption coefficients here in these regions here, these are all important regions for solar spectrum here. 800 nanometer, 900 nanometer, you can see here. All these are important regions here. 800, 900, 1000, these are all, I would like to absorb all these photons. But my absorption coefficients are very low. And because the absorption coefficients are very low, I have to make very, very thick silicon to absorb all those photons here. So these have implications for actual design. If the time permits, later on in the course, we'll look at solar cells in more detail here. All right, look at gallium arsenide in contrast. Gallium arsenide is a direct bandgap semiconductor. Its energy band diagram is shown here. This is the top of the valence band, and this is the bottom of the conduction band. You can see a direct band gap here with a gap of 1.42. Will gallium arsenide be a good semiconductor for solar cells? What are the good points and the bad points? What is a good point? It's a direct band gap, and therefore I'm likely to see higher absorption coefficients. Okay, I don't require a phonon to come in and help in the absorption process here. So I'm going to see higher absorption coefficients, which means what? I require thinner gallium arsenide to absorb. But what will be the drawback? Maybe the drawback that you're seeing is 1.42, so I'm going to miss more of the wavelengths. A lot of the wavelengths, the higher wavelengths, I'm going to miss them. Much more than silicon. Silicon was 1.12, so silicon could potentially absorb a lot more than compared to gallium arsenide. Anyway, you can see here, these are the absorption coefficients for silicon here. The only thing that I would like you, you can see here, gallium arsenide is 1.42 or so. So this is where absorption is beginning to happen. And you can see the values. Once it begins to happen, you can see the values are all 10 to the power 4 or above. Okay, so gallium arsenide is a strong absorber. The reason being is it's a direct bandgap semiconductor. And aside from that, of course, the nature of the semiconductor also matters. That is there. But direct bandgap contributes to a higher absorption coefficient. Okay. All right. Our interest is in generation. Absorption coefficient is important, but we would like to know, for example, let's say if I focus on a particular part of the semiconductor, how many carriers are generated here at this particular point? How do I calculate? Well, Ix, we say that the light intensity is exponentially decaying. And I would like to know in this small element, the X here, how many carriers are generated. Well, then you know that the decrease in light intensity as I go from X to X plus delta X will be equal to delta Ix equal to minus alpha I naught and so much here. The decrease in light intensity does what? Which means those photons have been absorbed, and each photon will give rise to one electron and one hole pair here. So how do I convert this? Intensity, as all of you know, is units are watts per centimeter square. So I have to convert it into number of photons. So what should I do? Number of photons which are incident per centimeter square would be how much? Well, I need to divide it by the energy of each photon, right? So that's what I do. So note, so I naught exponent minus alpha x is what? Is simply Ix at that particular point. So this equation can be written as alpha Ix times delta x here. And therefore, in that small element delta x, if I divide it by h mu, I will get the generation rate. Right? So alpha Ix divided by h mu is nothing but the number of photons that were absorbed in this small element dx. Once I divide it by energy, number of photons absorbed per centimeter square per second. Okay, so that's how I find the generation rate here. So the units of generation rate are carriers generated are percent. This I have divided it by delta x also. So it is the number of carriers generated per unit volume per second. So centimeter cube and second inverse here. All right. So suppose I take some numbers here just to get in mind what is this generation rate. Suppose I take 550 nanometer of spectrum, of course, which is normally incident is a broad spectrum. But suppose I take a light of wavelength 550 nanometer. I take an incident power of around 10 milliwatt per centimeter square, some typical values. Then if I plug it here with the alpha that I can read from silicon graph here, alpha I can read for that particular value here from the graph. And if I take that particular alpha, I take this kind of intensity, I take h mu corresponding to 550 nanometer, my generation rate comes out to be 10 to the power 20 centimeter cube second. Okay. So that's the total number of electron hole pairs which are being generated here. Of course, if you have light intensity smaller, it would fall. And I can have light intensity which is larger than this, then the number is going to change as well. But this is a number to keep in mind. Generation rate is 10 to the power 20 per centimeter cube per second. So if I have like if I have a piece of silicon and solar radiation is incident, you may have this kind of a number. Or this is 10 milliwatt. A typical solar radiation, the standard is something like 100 milliwatts per centimeter square. Okay. So that's the number to keep in mind. So that's how now electron hole pairs are being generated through the optical process here. All right. So that's optical generation. So the idea is light intensity is coming in and decaying inside the semiconductor, which is described by absorption coefficient. For each semiconductor, absorption coefficient is a function of wavelength. We can measure it. And then once you have that, then you can very easily calculate what the generation rate is. Another important point to keep in mind is generation inside a semiconductor will normally be non-uniform, as you can see here. If the light is incident from here, I'll have a lot more generation here. As I go deeper, my generation rate will vary. Okay, so generation rate is in general a function of x. I'm not going to have uniform generation rate all over the device here. Why? Because of this kind of a nature here. Okay. All right, a different generation process. So we talked about optical. There's another generation process which is called impact ionization. Here, note that what happens here. You can see the bands tilted like this. What do they indicate? Bands are not flat. A slope in conduction band, a slope in valence band, what does it denote? Electric field. So now if I, so these bands are tilted a lot. So there's a large electric field. All right. So now imagine this electron that I have. Suppose this electron enters this high field region. Somewhere inside my device, there's a high field region. And the electron enters this high field region. What will happen? It will start to move down, right? It will start to move down. And as it moves down, what can happen is it can then take an electron from here and promote it here. The excess energy, note that the electron is accelerating, right? It's accelerating. So the energy that it lost from here to here, what it can do is it can create another electron hole pair. Why? Through a process that we call as impact ionization. It's sort of the electron is transferring its energy to the lattice and creating another electron and another hole pair. Another hole here. Okay. So it's ionizing. All of you know, if you ionize a gas, what does it mean? You rip an electron out and you leave a positive gas atom, right? So it's something similar. Here is an electron, and what you have done is this particular electron has ionized your silicon by ripping an electron, but it doesn't rip the electron outside the lattice. It just brings it to the conduction band here. So now you can see here, I've created an electron and a hole pair. A generation has occurred. A generation of an electron hole pair has occurred through a process of impact ionization. The electron transferred its energy to the lattice and created this here. This, of course, you would expect to vary with the electric field. The larger the electric field, the more the impact ionization. And we describe this particular process using this equation here. We say that the generation rate of electron hole pair due to impact ionization is proportional to a constant which is called the impact ionization constant here. Okay, coefficient for impact ionization, and multiplied by number of electrons. Jn by q tells us what? Number of electrons which are flowing, right? So if I have Jn by q tells us number of electrons flowing per centimeter square per second, and these electrons then cause impact ionization, and what is the probability of causing impact ionization is described by alpha n. So these many carriers then that will be generated here. Now it's not just electrons which will cause impact ionization, holes can also cause impact ionization. So imagine a hole here, hole was moving up, right? A hole was moving up, and the hole can then cause an impact ionization also. So the net generation rate due to impact ionization is alpha n Jn by q plus alpha p Jp by q. So it depends on how much current is flowing. The larger the current here, and the larger the impact ionization coefficient, the more the generation rate. So this is the simple model that one uses for understanding generation due to impact ionization here. All right, you can see here the units here. The current would be Jn by q would be number of electrons flowing per centimeter square per second. Generation rate is per centimeter cube per second here. The units are alpha n is centimeter, 1 by centimeter here. So ionization coefficient, this ionization coefficient represents the number of electron hole pairs generated by a carrier per unit distance traveled here. That's the interpretation here. All right, so impact ionization, as we can understand, will happen if the electric field is large. And for silicon, a very simple model that you see for impact ionization for electrons here. Alpha n is 7 times 10 to the power 5 exponent minus 1.23 by field. F is the field applied here. Now, the alpha n then is a function of field, as I've been saying. If the field is large, impact ionization is large. If the field is small, impact ionization is small. Now, I'm calculating a value here. I'm trying to find out what is the field that I need to obtain a impact ionization coefficient of 10 to the power 4. Okay. What is the meaning of 10 to the power 4? 10 to the power 4, remember the units are centimeter inverse. So what it says is, when I apply a field of so much, my impact ionization coefficient reaches a value of 10 to the power 4. And 10 to the power 4 means that if my electron travels a distance of 1 micron, it will create 1 electron hole pair. Okay, 10 to the power 4 translates into 1 micron in terms of centimeters. So the probability of impact, the probability that a electron causes impact ionization is alpha times dx. Okay, alpha times dx. Okay, and then when alpha reaches 10 to the power 4, and if I multiply it by 1 micron, you can see the probability is reaching 1, which means that if my electron is facing a field of 3 times 10 to the power 5 and it travels a distance of 1 micron, is going to create, the chances are that it's going to create one electron hole pair. So it's sort of a critical field that people take for onset of impact ionization. Below this particular field, impact ionization is small. It doesn't have that much effect. Above this particular field, impact ionization is large and then results in large change in generation rate. Okay, so this is the critical field that people take where a significant amount of impact ionization occurs. And remember, impact ionization, what will it do? Suppose you have a piece of semiconductor and you have very little current flowing through it. Imagine a PN junction in reverse bias. Very little current flowing through it, reverse bias here. But there's a small amount of carriers that are flowing, right? Now imagine that I have applied a voltage large enough so that the field is close to this value or a little larger. Then what will happen is an electron, very little electron which enters here, it moves in, creates another electron hole pair. These two electrons then move in further, then they create more electron hole pairs, and therefore we have what we call as avalanche multiplication. And therefore I can have very high currents, and this is what you know as breakdown occurs. So this field that you see here is a field. If you apply fields larger than this, and all that, breakdown is going to occur in your normal semiconductor. These fields will cause significant impact ionization, and therefore you will start getting current, large current, due to this particular process here. This field here is obviously then important. If breakdown is harmful for you, you don't want carriers being generated due to impact ionization, you would like this field to be large. Now, and that's where you can see the values here. The values for silicon Impact ionization field is 3 times 10 to the power 5. Critical field is 3 times 10 to the power 5. For gallium arsenide is comparable 4. Obviously, you can imagine that it would depend on the energy gap. If I have a smaller gap, I need less energy to ionize my atom. If I have a larger gap, I need more energy to ionize my atom. Okay, so for silicon is 3, gallium arsenide is 4, diamond 100. You require 10 to the power 7 volt per centimeter to cause significant impact on ionization. For diamond is 100. For silicon carbide is 25. Okay, so you can see these numbers, and the numbers are, you can see how they're correlating with the energy gap here. Diamond, the energy gap is 5.5, silicon carbide is 2.9. Now, the reason why I put these numbers here is you can imagine that these numbers are important for devices which have to operate at very high voltages. There are a lot of devices, where the voltages required are maybe 1000 volts, 5000 volts. Okay, especially in the power electronics area, where you use it for handling high voltages and currents, you require very high voltages here. And there you can see the trouble that silicon would face. Silicon is 3 times 10 to the power 5, right? And now you want your silicon device to work fine at 1000 volt. What do you have to do? 1000 volt means what? I have to keep the field below 3 times 10 to the power 5 to prevent impact ionization. So 1000 volt, then how thick the semiconductor device will become? Because you have to apply 1000 volt, and 1000 volt divided by thickness has to be less than roughly 3 times 10 to the power 5. So it becomes a fairly thick device, right? And if it becomes a fairly thick device, what will be the implication? That's in the reverse bias, but in the forward bias, when you want a lot of current to flow, you have a very thick device. So a lot of voltage drops will start occurring. So you get into all those problems here. So you can see why a lot of people are now working on silicon carbide. It's a very attractive material. Silicon carbide gives you a critical field which is, sort of almost like 10 times larger than silicon. 10 times larger than silicon. So I can build my high voltage devices much readily using silicon carbide, provided I just look at the critical field. Of course, to build a viable device, many other things are needed. You need to be able to dope. The costs are there, and many other things are there. But purely from the point of view of breakdown and critical field, you can see here silicon carbide is very attractive. Diamond is even more attractive. Okay, but then of course diamond is expensive. Band gaps are very large. It's not that people are exploring diamond devices on these. These are of course not these are synthetic diamonds. Okay, diamond films that are deposited. All right. So anyway, so the point is impact ionization is another source of carriers. If the fields are high, I'm going to get impact ionization in my semiconductor, and electron hole pairs are going to be generated, and especially if the fields are larger than critical field, which have been measured and to some extent can be calculated also for different semiconductors here. And this is the model that we use here: generation rate due to impact ionization. All right. Let's look at recombination then. So we've looked at two major processes: optical absorption leading to generation and impact ionization. Recombination, now we are talking about the opposite process here, electron falling into a hole and recombining here. One of them is what we call as band-to-band recombination, which means the electron directly falls into a hole without without going through any intermediate state and recombines. Okay, so this is what we call as, let's see if I have a picture. Okay, so directly falls into that, and we call that as a band-to-band recombination here. Okay, and typically when that happens, it's also called radiative recombination. When an electron, without involving anything else, directly falls into a hole, the excess energy is released in the form of a photon here. And the recombination rate is modeled as some constant here, depending on the nature of the material. N and P are the electron and hole density minus Ni square here. Okay, so you can see that if my system is in equilibrium, Np is equal to Ni square, I don't have any net recombination. If the system is out of equilibrium, which means Np is more than Ni square, then I will get a net recombination. And the route for this recombination is direct band to band, from conduction band to valence band here. And this is something that one can get from, for different materials. These are constants that one can obtain here. Many times what will happen is, let's say you have an N-type semiconductor. Okay, you have an n-type semiconductor, and in that n-type semiconductor, let's say you have created excess carriers. Okay, you have created excess carriers, which means n0 is equilibrium and p0 is equilibrium value. And let's say by shining a photon, you create excess electron, delta n, and you create excess holes, which is delta p. And because you're creating through an optical process, for every extra electron, you get an extra hole also. So delta n equal to delta p. My semiconductor is n-type. N-type meaning n0 is much larger than p0. All right. Now, so then the recombination rate will be gamma. N will become n0 plus delta n. P will become p0 plus delta p minus ni square. Now, let me look at a case where what we call is as a low-level injection. Low-level injection means these excess carriers that you see here, delta n and delta p are small. Delta n and delta p are small compared to n0. See, n0 is the normal carrier density inside my device. Delta n and delta p I've created through, let's say, optical process generation. And what we are saying is delta n and delta p, both of them are equal, but they're small compared to n0. So then you can see here, what I can do is, because n0 is large, and if I multiply them together, then I can write R approximately as gamma n0 delta p. What I've done is, you can see here, you will get a delta n and delta p second order term, which we have neglected. We've kept only the first order terms here. So one can write R equal to gamma n0 delta p. And this further can be written as R equal to delta p by tau. So net recombination is equal to the excess hole density divided by a lifetime. Lifetime is equal to 1 by gamma n0. So this is a very simple model. If you have optical absorption, if you have a band-to-band recombination, I can model recombination as simply recombination is equal to how many excess holes are there divided by a lifetime, and lifetime is gamma times n0. Lifetime depends on the doping of the n-type semiconductor. The larger the doping, the smaller the lifetime. Okay. So although this is a general expression that we have, from the general expression we can get these simpler expressions. Okay. Mm-hmm. Yes. Always ni square in equilibrium. Yeah, it is 0 in equilibrium. That's true. I don't have any net recombination. There's no net recombination. Note that is cancelling. So what is happening is, I am getting what does ni square type represents? It represents a generation term. And np represents a recombination term. So they're balancing each other. Okay, so this is describing a net band-to-band recombination rate. Net band-to-band recombination rate. Note that if I don't apply any external excitation, I am going to get some optical absorption, which will promote from, if I take a semiconductor, there are some photons around in a normal thermal equilibrium. So I'm going to get a generation rate. This describes a generation rate. And I'm going to get a recombination rate. The net cancel each other. So at equilibrium, R equal to 0. And so it describes a net rate. Net recombination due to band-to-band process. Okay, it's not simply, if you just look at the first term, yes, that's the recombination only, pure recombination. Okay, but this is the net rate here. Okay. Another process is called Auger recombination. Here, note that what is happening is an electron falls into a hole here, and note that excess energy is released. In the previous case, the excess energy was released in the form of a photon. In this case, two things can happen. The electron falls into a hole and gives this excess energy to another electron, which then goes into a higher energy state. This is in the conduction band. Of course, it goes into a higher energy state, and after that, what will happen to this electron? It will lose and come back, to the conduction band here. So what is happening is electron falling, recombining with the hole, excess energy being released to an electron. Another thing that can happen is electron falling into a hole, excess energy being released to another hole. Both these are called Auger recombination. How do we model it? We model it using this particular process here. Recombination rate is some constant, n times p square minus p ni square. What does this first part represent? Which part do you think it represents? N into p square. Recombination is N and P. Can you see here? Recombination requires what? A hole, and it requires another hole, because you require this hole for recombination, but you have to release this energy to another hole here. And that's why you see here a P square. And it requires obviously the presence of an electron, and that's why you see N into P square here. And this part is what? This part is the to take into account the fact that net recombination at equilibrium is 0. Okay. So this is this part here. What about this part? In this case, the electron falls into a hole and releases its energy to another electron. So how should it depend? It should depend on N square, and it should depend on P. And that's why this particular part is there. N square and a P. Okay, so this particular recombination is then modeled in this particular manner here. Some constants here, Np square minus Pni square here, Pn square minus N into Ni square here. So that's the Auger recombination. It typically occurs when you have heavily doped, when you have high doping here. Because note that it requires the presence of another electron. And there's a strong dependence on P square, or there's a strong dependence on N square, and these become important when you have heavy dopings. All right, last of the recombination mechanisms, and the most important for silicon, which is what we call as the Shockley-Hall-Read recombination. Shockley-Hall-Read recombination, named after people who first published this particular work, Shockley-Hall, and these are their surnames of the 3 people who first described this process in detail. So what you have is, note that this recombination takes place through a defect level. There is some impurity which causes a defect level, let's say, which is ET. Okay, so there's a defect level inside the energy gap. Now, this defect level can do the following. It can capture an electron. Okay, the defect level can capture an electron. That's one process that can occur. A defect level can also, whatever electron it had captured, it can emit it back to the conduction band. That's another process that can occur. A defect level, then, these are processes showing the interaction of defect level with conduction band. A defect level can also capture a hole, and a defect level can also emit a hole back to the valence band here. So a defect level's interaction with the semiconductor occurs in these 4 distinct mechanisms. It can capture an electron, it can emit the electron back. It can capture a hole and can emit the hole back. Okay, these are the 4 things that occur in a interaction of defect level with conduction and valence band. Now imagine there is some defect level which does only this. These processes the other 2 are not significant. All that it does is it captures it or then releases it back. We call such a defect level as a trap. Because when it captures it, the capturing process is sort of easy. Why? Because it's lower in energy. Releasing it back is going to be difficult because it's higher in energy. So what it may do is it may capture it, keep it for a long time, and then release it after a long time. And therefore, what is it doing? It's sort of trapping the electron. The electrons which are there in the conduction band, they get trapped here, stay there for a long time, and then they may come out. Okay, because these are random processes here. So we call such a defect level as an electron trap. Its interaction is primarily with the conduction band through these processes. I can have another defect level which acts here as a hole trap. It can capture a hole and then it can emit a hole back. So it acts as a hole trap. But the defect level that we are interested in, it does the following. It acts as a recombination center. What does it do? It captures an electron. It doesn't release it back, and then it captures a hole. And in the process, what has happened? Captures an electron, captures a hole, and in the process a recombination occurs. The electron and the hole recombine via the defect level here. Okay, so it's as if what you can see is as if what is happening is the electron first comes here to the defect level, and from the defect level, capturing a hole is equivalent to saying the electron then falls back here into this particular state. So this is the recombination that we are talking about. This is the most important recombination mechanism in silicon. Every silicon sample that you will take will have some defect levels here, ET. You don't get a 100% pure semiconductor. There are some native defects, there are always some impurities, and these defect levels are always there. And they are the ones which cause recombination. in silicon. The optical process in silicon is not there because it's an indirect semiconductor. Auger recombination, we just said, requires a high doping, high carrier density. So that also normally doesn't happen. And the mechanism that is most important is this one, this mechanism, okay, which we call as a Shockley-Hall-Read recombination. Now derivations I'm not going to go through. The recombination rate via this mechanism is a long equation here. Okay, it's a long equation which shows how the defect is causing recombination here. The first part should be familiar to you. All recombinations you are seeing is Np minus Ni square. If I have an equilibrium, Np is Ni square, I don't have any net recombination. It's only when Np is larger than Ni square do I have recombination. So this is the normal part that we always see. It denotes how much out of equilibrium, how far you are out of equilibrium, this particular term. This term is, with the defect, there are several parameters which are associated with the defect. One of them is, what is this energy ET? Is this term here. Energy ET is here and here is entering. The other one is, associated with the defect, we have a concept of electron lifetime and a hole lifetime, tau p. 2 lifetimes are associated with this particular defect here, tau n and tau p here. The rest of them are straightforward. Once you have tau n, you have p plus ni, et is here, tau p is n plus ni, exponent et by kt. So it's a complicated expression. Many times we don't need this complicated expression. Often you will find, so et is measured from the intrinsic level. So often what we find is that, let's say, when we go into a p-n junction, we will find a case where I have, for example, if I'm looking at an n side of the p-n junction, I'm looking at excess holes in an n-type semiconductor here. So I'm interested in how are these excess holes recombining. So now what we do is the same thing. We write n equal to n naught plus delta n, p equal to p naught plus delta p. Because I'm looking at an n-type semiconductor, this part of the equation becomes more important because n is large as compared to p. So what we can do is we can neglect this first term altogether and keep only the second term. All right, we keep only the second term because n is large. All right, the other one is typically defects which we can see here, defects which cause efficient recombination are the ones which are close to the middle. They are the ones which cause recombination here, which means if they are close to the middle, it means ET, which is measured from EI, is almost equal to 0. Those are the defects which are very efficient recombination centers. So if it is 0, this term is simply Ni. And this term is simply Ni. Okay. Then what happens is, if this term is simply Ni, Ni will be much smaller than N. So I can forget about this term also. So note what is happening. First term I neglect. Why? Because I'm looking at an n-type semiconductor. In an n-type semiconductor, n is much larger than p. So first term I just forget about it. Second term, when I start to look at it, I'm saying ET is typically close to EI, or ET is 0, and therefore the second term is Ni. Ni is much smaller than N. And therefore all that I'm left with is what? Np minus Ni square divided by tau p into N. That's all I'm left with. After that, what do? I say n equal to n naught plus delta n, p equal to p naught plus delta p. We assume delta n equal to delta p. And then we assume that the excess carriers are much smaller than the normal equilibrium concentration. And with the simple maths, then it turns out recombination rate is simply equal to delta p by tau. So although the Shockley-Hall-Read recombination is a complicated expression, we finally end up, most of the time we end up using an expression for recombination rate, which is simply equal to the excess holes divided by a lifetime, which is tau p. And the lifetime depends on the nature of the semiconductor. Depends on the nature of the defect level, depends on how many, what the concentration of the defect level is. Okay. All right. So as usual, what we do is, let's have one problem quickly. All right. We have 1 minute. So the question that I'm asking is the following. We have an n-type silicon. N-type silicon. Doping is 10 to the power 16. And we are saying that there's a generation rate. Light is incident on this particular semiconductor, on this silicon. And there's a generation rate of 10 to the power 20 per centimeter cube per second. And we are assuming in this simple case that the generation rate is uniform all over. Same generation rate everywhere inside my semiconductor. I'm also giving you that whole minority carrier lifetime tau p. Tau p was what we just calculated is 10 microsecond. And I'm asking you, as a result of generation, what is the excess hole concentration? See, normally what would happen is if I don't have G, light incident, then we know that the electron density is 10 to the power 16, hole density is Ni square over Nd, which is about 10 to the power 4. That's the normal electron hole density. When I shine light, I'm going to get excess electrons and excess holes. And I'm asking, what is this excess hole concentration? How many excess holes are there? Whole minority carrier lifetime is 10 microsecond. Generation rate is 10 to the power 20. So you must be wondering where to start from, right? So let me tell you where to start from. Start from here. All answers that we will get, we'll get it from our equations. Start from whole continuity equation. We are talking about steady state. What happens to the first term? 0. We are talking about a case where this is ground, uniform illumination. We will not get any current. And further, there's no, even if you think that there may be a current, the current cannot vary as a function of x. Okay, because of the uniformity of everything here. So this term is also 0. So 0 equal to 0 plus GP minus RP. So what do you get? Generation rate must be equal to recombination rate. So what is the generation rate that we have given? 10 to the power 20. What is recombination rate? Remember this equation? Recombination, we say in an n-type semiconductor, we can model recombination as delta P by tau P. Simply all this Shockley-Hall-Read recombination that you see here reduces to this simple expression delta P by tau P. So now all you have to do is equate the generation to recombination. That's it. And find out what the excess carrier density is. So it's just one term here. That's it. G equal to R equal to delta P by tau. So all you have to do is multiply G and tau, right? That's all you have to do to get the answer here. All right. Why is this important? Can you see an application of this one? Can you see that this is a semiconductor device which is useful? Can be useful? Well, if I apply a voltage here at this particular point, I get a current. When I shine light, what will happen to the current? Well, I have excess electrons and holes. So what will happen to the current? The current will go up, right? How much will it go up? What is the value that you get for delta P? 10 power 15. Normally, what are the values here? Electrons are 10 to the power 16. Holes are how much? 10 power 4. Now what is happening? What will be the total number of electrons? 10 to the power 16 plus 10 to the power 15, which is almost like 10 to the power 16. Number of holes? 10 power 15. So will I get, if I apply a voltage, will I get some little bit of excess current? I'll get an excess current. And therefore, the excess current would depend on what the generation rate is. Right? And if you want that excess current to be large, what do you have to do to your semiconductor? You want this to be large. Right? Excess current depends on excess hole density. You want this to be large. What do you have to do? Well, one is you have to increase the generation rate. But for a fixed generation rate, what do you have to do? You have to increase tau P. And the issue is, how do you increase tau P? What do you think? How will you increase tau P? Recombination. Recombination is occurring due to what? Due to defect levels. I want high lifetime, which means less number of defect levels. So how do I get less number of defect levels? I have to make it very pure semiconductor. Very pure means very expensive. Right? So you end up with all those issues here. We'll discuss this in more detail. Okay.